Hey guys, so welcome to lesson one of online learning. I hope you guys are ready to go. Before we get started, we are starting a new unit and it is states of matter. Everything should be ready for you up on Microsoft Teams to download, including your notes and your practice questions. But before we get started on this unit, I do want to say we are done with stoichiometry. So if any of you were worried about that going forward, I decided to do no more stoichiometry this year. We're going to finish up with the last couple of units. We're going to do states of matter, and then we're going to talk more heavily about gas laws later on in the year too. So we're going to start some new units fresh, get these last couple of weeks wrapped up, and be good to go. Okay, so let's go ahead and get started on states of matter. Today we're talking about the kinetic molecular theory of gases. So after today, you should be able to describe the basic principles of the kinetic molecular theory of gases and explain where pressure comes from and what affects it. Okay, and if you feel like at any time you gotta pause this video, that's the beauty of online learning. Go ahead and pause, rewind if you need to, shoot me a question. Okay, I'm always here for you if you are confused. So let's get started. So the word kinetic means motion, and the kinetic theory of matter says that all particles of matter are in constant motion. So you may have a picture in your mind of gases, which we're going to talk about in just a second, of gases being in motion. They're floating around in the air, they're bouncing off the wall, they're always in movement, in motion. But turns out, even in solids, they're still in motion. But the movement in solids is so slight, they're just slightly vibrating in place, that it's hard for us to see. So we see those as solids, as not moving. But in reality, every single particle is in constant motion. So the word gas comes from the Greek word meaning chaos. Okay, so the Greeks observed gases and they knew that there was this random movement of gases going on. So they named it after the Greek word chaos. And numerous experiments have been led to figure out the evidence that suggests the following behaviors of gas particles at the atomic level. Okay. So we actually have three behaviors or theories that we're going to talk about that are most important and that have been solidified as the kinetic theory of gases. So first one is gases are made up of tiny particles of negligible volume. Now negligible means insignificant or very small. These gas particles are so small, okay? And turns out gas particles are far apart. They do not attract or repel each other. I know we've talked a lot about bonding throughout the year, but gas particles do not do that. That's why we had that whole column of noble gases on the periodic table not interacting in any of the bonding we've done throughout the year because they do not attract or repel, so they can't participate in bonding. However, there is attractive forces between the particles of solids and liquids, right? Solids like sodium chloride, liquids like water, those particles are bonding together. Okay, there are attractive forces there. So gas particles move independently of each other, and they're not participating in bonding. Everyone for themselves. And this is why gases expand to fill their container. If there's no bonding going on, they're always spreading out and expanding to fill their container. Okay? And another vocab word is the word diffuse. So the word diffuse means to move out. The best way to think about the word diffuse is if you go to your bathroom, turn on your shower super hot, and it creates all of this steam, and you shut your bathroom door, the steam is going to build up in there, right? All of that gas is going to build up inside of the bathroom. but as soon as you open the door, all of that steam is going to start to come out and move out. That is gas diffusion. Okay? And gases have no definite volume. Remember, they're there to fill up the volume of whatever container they're in. Gas particles also move very fast. This is number 2. Okay, gas particles move thousands of kilometers an hour. So, an example of this is when a bottle of ammonia is opened, it eventually spreads out and the gas smells up the entire room. Okay, and if you don't know what ammonia smells like, another example is dairies. Okay, so if you're driving by a dairy, okay, and you smell that cow smell, that's because all of the gases have been moving very fast from the dairy farm up to your nose. Okay, they've moved so fast that they've gotten to you, and those gases have spread out, and you can smell the dairy farm. So why does this happen? It's because the particles move randomly in small straight lines until they collide with each other and the objects in the room. Okay, so there's this randomness to the movement, and if they're left out in the open, they'll spread every which way, and that means those gases that smell will eventually reach you. All right, so we call this random movement that they do the random walk. Gas particles will move in a straight line until they collide with something else, like the wall in their container, or maybe another particle, and then they'll change direction and move straight in a straight line again. And they repeat this process over and over and over. Okay? It's a bunch of bouncing particles moving around, colliding with each other. And the last one, all collisions between gas particles are elastic. They don't stick together, right? They're not bonding. They do have kinetic energy. Okay, they're moving. They have that energy of movement, but this kinetic energy can be transferred from one particle to another, but is never lost. Okay, kinetic energy never goes away, but every time those particles bump into each other, they just transfer that energy from one another. Okay? So we have our 3 points for our kinetic theory of gases. Right? Gases are really tiny particles. They don't attract each other. Gases move very fast, thousands of kilometers a mile, or thousands of kilometers an hour, excuse me. And number 3, all the collisions are elastic, right? They're transferring that kinetic energy. So now that we know about the kinetic theory of gases, let's go ahead and talk about gas pressure. Gas pressure is caused by the collisions of gas particles with each other and the walls of their container. So collisions means pressure. Okay? Super important. Collisions equal pressure. As the number of collisions increase, the pressure will increase. Okay, just like you shake up a bottle of Coke, you are making those gas particles collide with each other more, and that means when you open it, right, the pressure has built up so high in there that the Coke wants to explode. Same thing happens with popcorn. So there's gas trapped inside the kernel of the popcorn. Once you make those collisions increase, the pressure increases and it explodes the kernel open, creating popcorn. So how do we get more collisions? Well, more collisions will result if there are more particles in a particular space, right? If I put 10 people in a room, they're not going to bump into each other that much. If I put 200 people in a room, they're going to bump into each other way more. So more particles in a particular space means more collisions. As temperature increases, pressure will also increase, right? We're increasing that energy, we're increasing the number of collisions that are happening with each other, and that's going to increase the overall pressure. So let's talk about what happens when there's no pressure at all. Well, there's a region of space where no gas pressure is exerted, and we call that a vacuum, just like the vacuum of space, right? There's no wind in space, right? No particles moving at all, no gas pressure. So that is a vacuum. Gas pressure is equal to 0 in a vacuum, so there's no collisions. And an example of this is peeps. Okay, so turns out you can find this video online, but if you put a peep inside of a vacuum chamber and you pump all of the gas pressure out, okay, that means all of the gas particles are going to stay in place, no collisions, okay, but as soon as you put that vacuum pressure back up, the pressure is going to increase the collisions and the pressure is going to crush the peep. The peep's going to get crushed by the pressure. So let's talk about atmospheric pressure. I'm sure you've heard of this. Okay, this is reported a lot in weather stations and weather channels. Okay, they tell you the atmospheric pressure for the day, and the abbreviation for this is ATM. So atmospheric pressure is the pressure caused by the air in our atmosphere. And this depends on weather and altitude conditions, so it's different in different places you go. But the general rule is, as altitude increases, atmospheric pressure decreases. So the air gets thinner as you go up. So if you go up in altitude, the atmospheric pressure decreases. That means there's not as many collisions. Those gas particles are really spread apart. And so every time you take a breath, you're not breathing in as many oxygen molecules as you're used to. So the air feels thin and harder to breathe. And just like most things in chemistry, we have standards, right? We have a standard pressure that we use in calculations. And standard pressure is the average pressure measured at sea level. So if you are above or below sea level, you're different than the standard pressure. And the standard pressure is equal to 3 different quantities, and they're all representing the same thing. They just have different units, and we can use those in calculations with pressure. So let's take a look at those. We have standard pressure as 1 atmosphere, as 760 millimeters of mercury, and as 101.3 kilopascals. Now we haven't talked about pascals yet, but that is a unit of pressure. Right, and the last thing I wanted to let you know about is how people measure pressure. Like, what is the tool used to measure pressure? And that's a barometer. So a barometer is a device used to measure atmospheric pressure. So you can see one off to the right here. It's also in your notes. Okay, back in the day, people used to use these mercury barometers to measure pressure. Now we have more technologically advanced barometers, so we don't have to touch this mercury anymore since it's so poisonous and can affect your brain and central nervous system. Okay, it's pretty harmful to the human body, but barometers are what we use to measure atmospheric pressure. So today, big info day, not a lot of equations today, but we have learned a lot about the kinetic theory of gases and about gas pressure. So go ahead and complete worksheet number 1. If you have any questions, message me on Remind or on Microsoft Teams so you can get some help. And make sure to take a look at lesson 2. And if you're finished with that, go ahead and move on to those quizzes. See you guys in the next lesson.